Assalamu alaikum. Welcome to the new topic that is known as insulation resistance of a single core cable. This is very important because this is also a property of the cable which determines its health, how good an insulating cable is, or we can say underground cable is. The more the insulation resistance, the more good health of a insulated cable is. So higher the resistance of the insulated cable, better will be the cable. So we'll first discuss or mm, see what is the insulation resistance. The cable conductor is provided with an insulation of suitable thickness so as to avoid leakage current, and the opposition offered by the insulation to the leakage current is called the insulation resistance of the cable. As I have told you that this is a good property of the cable. The higher the value of the insulation resistance, better will the cable, because it uh, it provides a resistant path to the insulation current, sorry, leakage current. The lower the value of the leakage current, good is the electric cable or insulation cable. So we have to calculate its value. Before going to this, okay, after this I will say more about this insulation current or leakage current. It flows from the conductor surface through the dielectric to the surface of the sheath. So it actually flows readily outwards from the conductor to sheath. Actually, since our motive is to provide the current or power to the load, and that in that case the direction of the current will be along the direction of the, or along the length of the conductor. But in this case you will see that the current direction is not along the conductor length, that is in this case into the plane of the page or out of the plane of the page, but in this case it is readily outward. It is actually not going to the load. That is why this is not good property of a dielectric material. Let us say conductor radius is r, small r, and the cable radius or the sheath radius is capital R, and the length of the cable is L. Before going into this, I will try to make clear to you that we know that the resistance in general is given by R is equal to rho L by A. While we know that this rho is the property of the material, is known as resistivity. How much resistance is offered by the material. Not resistance, we can say resistivity apart. It is independent of the length and area. And L is the length and A is the area. But we have to specify this L and A. This A is actually the area through which this current flows, or we can say it is the area perpendicular to the flow of the current. It is the area perpendicular to the flow of the current. Similarly, length is along the direction of the current. This is very important. For example, if we have this conductor and we know that its cross section area is like this, A, and its length is L, and the direction of current is like this is I. So in that case this length is same as this L and this area is same as this A. If somehow I am taking the same conductor whose area is again same, whose length is L, but the current direction is like this, then in this case we have to define this L and this A. In this case this L will not be same as this L and this A will not be same as this A, because I have told you that the area that is present in this relation R is equal to rho L by A is the area which is perpendicular to the direction of the flow of the current. So here also you can see that the area we can see is this much, not this much. I will see what is this, but it is definitely different from this. And the length in this case will be this much from here to here. This will be this length. That means in this case it will be diameter. So similarly in this case you will see that now the current direction from this conductor to this sheath is radially outwards. That means in this case length will be from this point to this point. So in this case it will be definitely R. So what is the area? Area is the total curved surface area of this conductor. That will be the uh, curved surface area of the cylinder. I can write it as here: R is equal to rho L by A, rho L by A, where L is the length through which it along which it passes. So in this case, let us first discuss. I have assumed at a distance x from the radius of the center of the conductor, and I assumed an elemental x ds, so that I will first calculate the resistance of this simple dx, and then I will integrate it to get the total resistance. So since the length is along this point to this point along the radial length will be the length of this current, that means this L will be equal to dx in this case. And what is the area of this element? I will write, make it over here again. This is a radius r and this is x. So this is a cylindrical curve whose length is differential length is dx. So the length of this L will be now equal to dx. The length along with the current flows, that will be equal to this dx. And what is the area? Area will be the curved surface area of the cylinder. That area will be equal to 2 pi r h, where in this case r is equal to x, that is 2 pi x into h, and L, h is the length of length of the conductor, actual length of the conductor, not the length through which this current flows. So this dx dri, that is the insulation resistance at x, will be equal to rho dx divided by 2 pi x dl, 2 pi x into L. So total resistance will be the integration from small r to capital R will be equal to rho dx divided by 2 by x into L. That will be rho divided by 2 pi L from R to dx by x. That will be equal to rho divided by 2 pi L ln of R by R. So for a different types of cable where rho is the resistivity of not the conductor, in this case it will be the resistivity of the dielectric material, because this current flows through the dielectric material. So for a same dielectric material, you will see that this insulation resistance is inversely proportional to the length of the cable. In the previous sections we have seen that the insulation resistance is usually directly proportional to length. In that case, because that length is actually the length along which the current flows, but this length is not that length along which the current flows. This length is actually the length perpendicular to this length the current flows. That is why in this case you will see that the length comes, or we can say the resistance is inversely proportional to the length of the conductor. Thank you.